लगाना पड़ेगा, किसी बोल
मेरे को परमिशन देना पड़ेगा फाइल शेयर करने के लिए. गुड मॉर्निंग एवरीवन. या आइतेन.
गुड मॉर्निंग सर. यस सर. थोड़ा ब्रीफिंग हो जाए सर प्लीज सर. Good morning to all. Myself Dr. Vidyakant Shukla going to introduce a man of still beginning never ending, renowned Professor Brijesh Kumar, who is a senior faculty in the Department of Electronics and Communication in Madan Mohan Malviya University of Technology, Gorakhpur. He has done his PhD from IIT Roorkee on the topic Organic Thin Films Transistor from Low Power Digital Circuits and Display Applications. His research work is very useful in the field of science and technology, science and engineering. He has a vast experience of teaching to the UG and PG students. Except this, he has supervised 30 MTech and 1 PhD student. He is a member of many academic and professional bodies. Professor Brijesh Kumar has been very active in many seminars and conferences. He has published 59 papers in various international reputed journals. Overall, it can be said that his interest and his contribution in electronics engineering has made him a bright star in the field of science and technology. Now, I would like to request to Professor Brijesh Kumar, sir, please come on the stage. Thank you, sir.
Yeah. Thank you very much for a nice introduction. Yeah. I'm going to share my PPT.
Thank you, sir.
PPT is visible to everyone?
No, sir, it is not visible yet, sir.
Okay.
Yes, sir, not is visible.
Yeah. I think visible to everyone, no?
Yes, sir, not is visible, sir.
Yeah, fine. Thank you very much. First of all, really, it's my pleasure to be here for delivering invited talk on organic area, especially those who are interested in organic material-based devices and circuits. Is really this very useful talk. So, and later on also we can have some query, right? And those who are interested in work in this area also most welcome. So I'm going to deliver this regarding the recent developments, right? So what currently the organic material-based devices and circuits is still like we aware about MOSFET in 1960s and 65. Similar way, presently the organic material-based devices are, because my humble request to everyone, please consider this organic devices like one alternate, right? Option. It's not comparable to MOSFET. Beginning, I'm giving the statement is the alternative, another device which can be used for flexible electronics, flexible applications, right? So the topic for this organic material-based devices and circuits and its application also, I will share few applications during my discussion. These are the outline of initially what is this motivation behind the organic material-based devices and circuits, then little bit the introduction of electronic devices applications, and apart from that, I introduce in my talk what are the scope of research, so people can work in this area, because organic thin film transistors have low mobility devices, or I can say other words, it cannot be utilized for high-speed applications. It's very useful for display applications, especially backplane driver, right? Switching device for the display, especially. Right? So how can we improve the performance of organic material-based devices by considering layer material, different device structures, and because why we call it thin film transistor, because these devices layered structures based. So that's why. Another is based on the, because this device, because of the low mobility, these devices are having much larger dimensions. So people are working also on how to optimize the, or how can we reduce the size of device. So that also open. Then semiconductor and dielectric thicknesses people can consider for their improvement. And apart from that, various interfaces, because this organic thin film transistor is layered structure, so there will be a interfaces between electrode to organic semiconductor to dielectric, dielectric to gate. So there is three interfaces. So people can work on dielectric organic semiconductor interface, or contact electrode and organic semiconductor interfaces. Apart from that, I included two applications, another organic light emitting diode and organic solar cells in this. So these are the research group. So now, my PhD earlier, this one student is awarded the PhD in this same area, organic material, and recently another Sonam Tripathi also submitted the thesis, and third Sandeep Kumar Oja also in permitted to submit the thesis in this area. So one student worked on the organic thin film transistor performance optimization, another is different materials for the solar cell, and the third one is working on going to submit the thesis on organic light emitting transistors. So these are the just part of research. And I'm also having the collaboration with the faculty members in INOP, IIT Bombay, IIT Roorkee, Professor B.K. Kaushik ji there, Dr. Professor Manhas ji there, and Professor our Das Gupta sir there. So time to time we have and this amorphous semiconductor laboratory we already set up in MMUT. So where we can working on materials. Not still we don't have the facility of fabrication of devices of TFT or organic material, but we are working on the material here and NPL Delhi also. So just important part of this, where is this beginning of. So in 1970s, the Shirakawa group, they have developed the conducting polymers. So everyone is, I think, aware, just having the idea that pure insulators, pure polymers are insulators, right? So in late 1970s or late 70s, discovery and development of conducting polymer by the Shirakawa group created a new research field. So for thereafter 1979, Lee Kumar, using this conducting polymer, demonstrated amorphous hydrogenated TFT. Then thereafter in year 2000, the material developed in late 70s, conducting polymer, that material was polyacetylene. Initially, first material conducting polymer is acetylene doped with the boron and that. So for same work, they have created this group in late 90s, 70s, 1976, and for same work, they have been awarded the Nobel Prize in year 2000 in the area of chemistry. So that is really, and 1986 first organic TFT or other words using the conductive polymer thin film transistor was demonstrated properly. So that is the background for the main motivation behind the development of the conducting polymers in late 70s. So that the turning point for the organic or flexible devices. So here I given the comparison of three technologies. First, single crystal silicon that everyone is aware, MOSFET, CMOS, PMOS, NMOS, and thereafter amorphous silicon and organic TFTs. So if we go for temperature bias, temperature So single crystal-based devices are fabricated more than the 1050 degrees centigrade. So we aware about that. The main cost for the ultra clean room is how to control the temperature of that furnace, that environment, and ultra clean room. So huge amount is required to set up the fab lab in case of MOSFET or single crystal based silicon based. Whereas amorphous silicon and organic TFT especially, so amorphous silicon based devices are fabricated less than 250 degrees centigrade, where the substrate material, the glass is the substrate material. But in case of organic devices, organic TFT, organic thin film transistor, it can be fabricated in a just ambient temperature. We can set up the laboratory in just room, right? So that and where the substrate material is used, paper or plastic can be for the mechanical support only. So that is the big advantage. So cost of the fabrication of organic thin film transistors is much lower than in comparison to MOSFETs. So that's why these devices are used. Even this because of the low temperature fabrication, so cost of the fabrication is much lower. So that's why the product of developed using this organic TFT, organic material based, is much lower, having the much lower cost. Another, if we go for the comparison between the performance, this side is the given that this graph you can appreciate, right? This side is the cost and this side is the performance. So you can decide your priority, you want to the cost your priority or your performances, right? So based on that, so here we can see in case of organic, my this everyone is bottom is there.
Yes, sir.
Okay.
Yes, sir.
Yeah, fine. Thank you.
So you may proceed, sir.
Yeah. So here we can see the cost and performance comparison. So if our target is low cost, right? If you see the market with malls where lakhs and lakhs items are there. So if you have the means 10 lakh of item, or where the you want to tag, right, that item. So you want a cost should be minimum. Currently using the barcode. If we go for the RFID tag kind of thing, then this organic based device is having the much lower cost, right? Few cents in comparison to 10 rupee or 20 rupee for the barcode. So if the cost of that 10 lakh items can be reduced, right, by, so this people prefer to go for organic. If they want to high speed application, high performance, ultra low power, then go for silicon. So, but you compromise with cost. Cost is much high in comparison to this. But for the if you want to compromise with cost and your target compromise with the performance, then you can go for low cost application. So that is here you can see the cost is for organic is this much, and whereas the cost of silicon is so much high. Right? So what is the means merit of this? Here you can see this side. Organic devices consist of thin film structures. Apart from that, semiconductor especially. So semiconductor can be of either conducting polymer or small molecule. So small molecule having higher performance in comparison to conducting polymers, because conducting polymers are having much higher mobility in comparison to conducting polymer. Small molecule material based devices are having much higher comparison to. But as per comparison of mobility, so conducting polymer small molecule materials are having highest mobility around 15 centimeters square per BS. As we are aware about that, silicon based devices having 1350 centimeters square BS and a P-type. But in case of organic, P-type devices having much higher mobility in comparison to that N-type. So key interest in organic devices, number one, processing at low temperature. Another is low cost fabrication, because of the that we not do not require ultra clean room. So, and other is foldable, bendable, and lightweight. These materials are also having the compatibility with flexible substrate, whereas silicon based devices or silicon is rigid material, so we cannot compare with flexible substrates. And the substrates are paper, plastic, fiber, cloths, and foil. So nowadays a lot of people in the different countries are using smart cloths in the medical purpose. They are just having the gowns and all medical kits, and so they just patient can wear that, and different sensors are deployed in that smart clocks. So doctor can just get all the information from of the patient. If we can compare with the inorganic semiconductor and organic semiconductor, so these 5 parameters I have considered here. One is the temperature, the flexibility, process, and conditions and substrate. So we aware already, I discussed in my previous slide, that these materials, inorganic semiconductors, are having the range of fabrication is greater than 800, whereas organic semiconductor based devices room temperature. And flexibility, these inorganic semiconductor material fragile in nature, whereas organic semiconductors having flexible nature. And as per fabrication process steps, inorganic or silicon-based devices require multi-step photolithography. And in case of organic semiconductor, these can be of continuous direct printing. Right? Continuous direct printing means we have the solution in the that bucket, and with the help of a spin coater kind of thing. So, or large continuous direct printing. So solution can directly drop through the printer, and that can be possible only continuous process. Whereas in case of MOSFETs and all, multi-step photolithography is required. And as per condition or temperature requirement, ultra clean room is required in MOSFET silicon-based devices, where ambient temperature or room temperature or room ambient processing can be possible in organic. And substrate here, rigid glass, metal, or silicon itself. Silicon, heavily doped silicon is used as a substrate material, but in case of here, flexible plastic substrate will be used for the to provide, especially the purpose of in case of organic semiconductor, the purpose of substrate to provide the mechanical strength. Over that, we can deposit the organic semiconductor devices. Here, given the same just comparison between all three merit of organic over inorganic semiconductors. So here you can appreciate this here, right? So as for cost wise, right here, so to this having $5 right per square feet, whereas here you can see 10 almost 100 right dollars per square feet. So cost you can compare, so much lower cost in comparison to silicon based. Whereas fabrication cost is low capital because not require the ultra clean room, whereas huge cost and 1 to 10 billion cost is required to set up the ultra clean room. Right? And whereas you can see this device size, here device size can be possible 10 feet into roll to roll, means suppose somebody want to fabricate 10 feet length height by 50 feet. It's possible with organic material based, but whereas in silicon there is a limitation of only less than or hardly 1 square meter only. So that's why you can see if in case of TFT or silicon based, we have combined and 4 or earlier we only suppose we want to design a large display, then different TV and different 1 meter square by 1 meter square by 1 meter, 4 devices. Suppose we want to 4 by 4, right? Then we require different right size TFTs. Then combine that so that possible with the silicon only, whereas in organic devices, large means large area display can be possible. Right? So that is the major advantage of large display. Suppose for railway station, somebody want to display 10 feet by 20 feet. It's not possible with silicon. Right? If possible with silicon, cost will be much high. So that's why. And material bias, flexible plastic substrate and rigid glass materials in this case. And earlier we also discussed ambient processing, ultra clean room, right? And here continuous direct printing and this multi-step photolithography. So this just comparison between organic electronics and inorganic electronics or silicon-based devices. Now, because we aware about that, nothing is perfect. So here you can see the organic electron devices, right? All this organic electronics is not a technology competing with silicon, right? Because this having your low cost is low, right? And the fabrication cost also low. But as per concern of performance, right? We cannot compare with silicon. Right? So that's why organic electronics is not a technology competing with silicon. It is just another option where people can utilize this technology. But apart from that, what is the merits of organic electron devices? It intended for the innovative application that are either not possible or too expensive with silicon. As I earlier given the example of large area display. Okay. So with the organic is 10 feet by any feet length in anything, right? Can possible at lower cost. But if we go for silicon based devices, right? TFT, it's having much higher cost. So that's why it for innovative applications that are either not possible or too expensive with silicon. Organic semiconductor have brought exciting new opportunities for broad impact application requiring thin film architecture. So this can be utilized. OSC have appealed for a broad range of device applications, yes, where transistors is possible, diodes, organic solar cells, organic light emitting diodes, and sensors. Nowadays, a lot of work is going on in this area. IIT Bombay developed one that IC, and that IC few years back I attended that conference where I gone through that that chip can predict the means give the prediction about disease, and that cost hardly 50 rupee only. Whereas to identify to diagnose the disease, if you move to any hospitals, right, at least 5,000 to 50,000 to only identify the disease. So this lot of work is going on in sensor area, organic solar cell for lighting and light emitting diodes for the purpose of display organic light emitting diode, and for the purpose of lightning organic solar cells. So this broad given the listed here the few applications of organic material devices. So if we go for this here, we can say OTFT, right, and OLED technology this side, then LCD, then memory devices where flexible LCD, right, and here you can see this organic memory here, and sensor technology where image sensors are this image sensors are. So a lot of sensors are nowadays, lot of medical applications are there where lot of sensors are deployed in the human body, so that can give the signals for the means distant person are sitting, doctors are sitting. So with the help of sensors now, medical facility will be provided. Then OLED technology where you can see this flexible OLEDs, right, display, and another e-ink, right, electronic papers, right, e-technology here. Then IC technology, as I given the one example, IIT, the Mumbai developed chips based on this organic material, these devices, and smart this smart card RFID. So in any organization, in any big malls, right, lot of items are there. So where this organic material based RFID tag can be deployed. So cost can be reduced much lower. Right? Organic lasers, right? Optical technology, then biosensors and smart fabric, especially this smart fabric is used for medical applications especially. So these are the broad applications of organic devices. So people can take up and a lot of even in India, IIT Bombay is working in organic devices. IIT Kanpur having full-fledged laboratory, flexible laboratory there, and the Samtel Center is there in IIT Kanpur. So nearby people can contact to professors of IIT Kanpur itself, and Jadavpur University also working in this area. Now, this everyone is aware about this MOSFET. I am not discuss much. Only this diagram I included for the comparison of uh, operating principle. So, as we aware about that, this MOSFET is having the concept of formation of channel through inversion. Right? Having the concept of uh, inversion. We aware about in case of this MOSFET conducting or resistivity of the path between two contact source and drain is altered by voltage applied to the gate, right? And device is also known as voltage controlled resistor, where poles are repelled by positive gate poles, leaving behind negative ions and forming a depletion region. Apart from that, what is the inversion? Electrons are attracted to the interface and creating a channel, right? That is inversion layer. Be aware about that. Majority of that, this heavily doped your full substrate is there, but you can see these are areas, two areas heavily doped silicons. So where majority of electrons are there. So with inversion means minority carriers from the substrate material and few electrons participation. So this whole this conversion of this p type into n type. So that's why this strong inversion, low inversion is different thing. But in case of MOSFET, inversion phenomena is used for the formation of channel. Whereas in case of MOSFET here, now you can appreciate. In case of MOSFETs, organic thin film transistor, in case of OTFT, right, this organic thin film transistor, right, here you can see why we call it this organic thin film transistor uses organic semiconductor material rather than silicon as a channel material. Right? Rather, silicon as active layer or channel to current flow. Here you can see this, right? So this material is organic semiconductor, right? This channel is 3D structure. You can see here channel active layer. So this active layer is either conducting polymer or a small molecule, right? So it consists of thin film structures and usually named as, right, position. Here you can see named as based on the basis of relative position of source and drain and gate, right? So here you can see, right, in 3D structure of OTFT, source and drain and gate here bottom, right? And this substrate, this material is substrate material, right? So in case of 2D, here you can see, right, the channel is formed through the accumulation, whereas in MOSFET, inversion. Right? So that is the operating principle difference between OTFT and what is the accumulation. Here you can see when we have this gate voltage not applied, so then off state. If it is gate voltage is applied between source, this here source, right? This is this side is drain and this gate here, right? So and this material here considered p type, right? This material is considered p type material here, right? So if we apply the negative gate voltage from here, negative gate voltage here, suppose minus 5 volt, right? Minus 5 volt, right? Applied here. So what this minus 5 volt, right? We aware about this dielectric material. This dielectric material is there. So now working as a parallel plate capacitor. It is working as this negative side, and this negative is attracting positive, right? Holes from injection, right? Injection, right? Carriers are injected because of the. So what is the purpose of BGS and BDS here? BGS is contribute to formation of channel, whereas BDS is participate in the flow of carriers, means current flow. Okay? So this accumulation of these carriers holes nearby the near to the interface of this OSC material, right? Organic semiconductor, and this your dielectric. So interface is here, right? So most of the carriers holes are accumulated near the channel. So that's why we called it accumulation, right? Phenomena. Right? So if we increase the BDS, current will flow from source to drain side. So this is the current flow or charge transport phenomena in OTFT. Now, somebody want to improve the performance of organic TFTs, right? So what can be the possible to have high performance OTFT, right? High performance OTFT. So people can work in to enhance the. So what should be there? Current, drain current or on current should be high. Then mobility of that should be high to get the high performance device. Threshold voltage should be low to operate at lower means have the to operate at lower voltage, right? Transconductance high, right? On-off current ratio. What is the beauty of this device? Because these devices are large dimension device, so we are aware about I on Y, right? I on Y, I off, right? I on Y, I off. So this ratio is called current on off ratio. So because of the large dimension device, this OTFT, this is much lower. So that's why ion off ratio of OTFT is much higher in comparison to MOSFET. We are aware about the typical value of this ion of current ratio in MOSFET is 10 to the power 6, whereas people reported in literature almost 10 to the power 9 for OTFT. So it is much higher. So this is very useful for display devices, especially, right? What in case of display we want? We want my device in case of off, display is off, no leakage current should be there. So because of the large dimension or because of this concept, high on-off current ratio, so how we can get high on-off current ratio? Either we have high drive current or lower leakage current. So that's why this is much useful for display application. Means immediately we want on or off. So if we have this concept, high on-off current ratio, so this is helpful for the display. Then sub-threshold slow, then contact resistance is low. And what is the area of research where people can work in organic transistors? First one is the layered material. So layered material can be developed with the joint group of chemistry persons and physics persons. So good material, if available, or high mobility material will be available, then obviously the performance of OTFT directly enhanced. Then different device structure. Still, lot of work people are working on device structures, single gate, dual gate, cylindrical, as we have gone through the silicon. So same concept. So here in previous also we have gone through same Shockley equation is applicable for the OTFT also. Only the difference is these devices is only large dimension devices, right? So this different device structures, then channel length, electrode thickness, and OSC dielectric thickness interfaces. So these are the research scope for the organic TFTs. So one by one, I am just a little bit discuss. Few reported results are included in my discussion. So here, first one is the effect of layer material. So what kind of layers is there in different organic devices? So material at different layer affect the device performance significantly due to difference in their properties, right? What are the properties as we aware or in silicon also? So here you can see energy band gap, right? Based on that layer material, right? Affinity, temperature tolerance of that work function, supporting fabrication process. We are using thermal evaporatant or spin coating. So this also the type of method used in fabrication also affect the performance of the device, right? Because by using organic thermal evaporator, right, high performance device can be fabricated in comparison to spin coating. Then adhesiveness at lower layer. So these are the few property where these property can be considered. Electrode material effects. Right? Electrode material effect. Yeah. Then electrode material effect. So charge injection and extraction with the help of that. And we aware about that. If we go for this diagram, you can see here this electrode, right, and this OSC. So if we don't have the material of matching, suppose the work function of this electrode is somewhere 5 electron volt, right, and OSC like a pentacene, right, this 4.9 electron volt, right. So here the work function difference or barrier height is, what is the barrier height for this? 5 electron volt and 4.9 is 0.1, right? 0.1. Where if we don't have this gold, this 5 electron volt around gold, right? Gold have the this work function around 5.1 or 5, I think 5.1. So here 5.1 electron volt and 4.9, 4.9 for the pentacene. So here you can see the barrier height is 0.2. If somebody using, right, instead of here the pentacene 4.9 and here say suppose some other material that having work function of 7, so much higher the barrier height, so the injection or carrier injection is much difficult. So that's why. So this means this charge injection and extraction, right? So material of electrode material affects, right, charge injection and extraction. If we don't have the matching material of OSC and electrode, so that's why this contact OSC interface affect the performance. Means that allow the injection easy way or typical way. So that's why. Then here you can see substrate materials, right? Flexibility of device depend on if substrate is not compatible with organic material. Then fabrication process. Right? Then this side, right side, you can see organic semiconductor affects what? Charge accumulation, right? Self-trapping of carriers, device mobility, and solution processability. Because this organic material, every material is not soluble with every solvent. So that's why, right? So selection of means solvent for the organic semiconductor material also affect the performance. Then come to the dielectric material effects, device capacitance. We aware about that concept of COX is equal to, right? So this epsilon naught epsilon r, right? Epsilon r over TOX, right? This capacitance per unit area, right? So here you can see this epsilon naught is constant, whereas this epsilon r, right? So the permittivity of material also affect the interface, right? So that is there. Right? So that's why device capacitance, right? Threshold voltage, right? Dielectric OSC interface, and thickness of that is dielectric material, and dipole formation. So here we can see the electrode material effects, substrate material effects, and organic semiconductor and last one is dielectric material affect the performance. So by choosing, right, these four kind of materials, right, for the different layers of the device can improve the performance of the device. So effect of layer material. Now, various organic materials are there according to application, according to demand of work. We can choose organic materials is classified in three category as we aware of in the inorganic also: semiconductor, electrode, and insulators, and non-conducting polymers. Right. So then small molecules and conducting polymers. There further, small molecule and conducting polymer is classified p-type small molecule and n-type small molecules. Right? Please, in between, anyone want to any query? Please, you can discuss. Right. So it's then
Okay, sir.
yeah, conducting polymers, p-type conducting polymers, and n-type conducting polymers. So similar classification as we aware in inorganic. Right? So here I have given few examples of organic semiconductor. Right. So broadly, organic semiconductor is classified in two category. First one is the small molecule, another is conducting polymers. Right. So this side, if we go for small molecules, then just मैं डिपार्टमेंट में लेके ऑनलाइन लेक्चर ले रहा हूँ. So small molecule is here. This side you can see if we can compare with the small molecule and conducting polymer. So small molecule having the low molecular weight, right, and a high mobility in comparison to conducting. Right. P-type materials examples are pentacene, right, and this further the pentacene is improved, so that called the TIPS pentacene, then tetracene. These are the P-type small molecules. All three in this P-type small molecules, right? Where these are the P-type conducting polymers, right? P-type. So this poly-3-hexylthiophene, poly-3-alkyl-thiophene, and polytrialamine. So PTAA. So these are the examples of P-type conducting polymers. This side is P-type small molecules. Then fabrication techniques for small molecule, thermal evaporation and vacuum, right, is used. So these small molecule kind of powder form. So this required some solvent, good kind of solvent. So pentacene used the alcohol and benzene as a solvent. So this here we can see this thermal evaporation and vacuum. So here you can see the this chemical structure of pentacene, where group of 5 benzene ring, right? Benzene is called formed the pentacene. Whereas this side low cost solution process used as a fabrication technique, and this P3ST chemical structure. Then based on these materials, right, few examples I have given here. So one or two I discussed here. Here you can see this. So earlier also I discussed what is this. This capacitance can be epsilon not epsilon r over Ti. So this Ti is the thickness of the insulator. So now with the help of this material combination, to fabricate any device, we required organic semiconductor material, dielectric material, source and drain, and gate. So here we in this table I have given the same sequence of the material. So here you can see organic. First example, this pentacene aluminum oxide, right, is dielectric SAM of the this. Then source and drain is used as gold, and gate material is aluminum. So similar this combination, and find out the values, dry current, right, and here you can see this 5.1. Please don't confuse with this negative, because BGS and VDS both are negative applied to the device, because p-type device, right? So that's why this negative value. Negative is representing only because of the BGS and BDS both are negative because of the p-type material. So if it is n-type material, it should be positive, right? So in comparison to that, silicon-based devices, silicon-based devices having much higher right current. Because of the poor mobility of these devices, this current is quite low. Yeah. So here these are the transfer and output characteristic for same material by this using. Right? Now, similar other examples here we can see these are the performance parameter extracted for the device. These are the performance parameters, right? Extracted for the, as we aware in the case of MOSFET. So same Shockley equation is applied here, right? Only the concept pool and Frankel model is applied, right? Using the Silvaco. These all results are we have extracted using the Silvaco tool, right? These are the Silvaco tool, and I have given in this table few references because these are the fabricated work. Right? Similarly, based on different material, so we can have here you can see this, right? One paper reported in 2018, right? That reported the mobility of 2.4, and the other place you can see lower, much lower mobilities. So that's why these devices are not applicable for high speed or gaming point of view, right? These devices are very much useful for display, where the speed is not a matter. Another type is thin film structure. So what is the device, right? Different device structure, right? OTFT structure. So as earlier I discussed, structures can be single gate, dual gate, right? And cylindrical, right? But still none one is reported, there's no organic material waste FinFET. So people can think over it, right? So here OTFT can be classified, right? Single gate itself have the different classifications, right? So here I given the example of single gate based. So single gate, in case of single gate, top gate can be possible or bottom, right? So top gate further classify with, here you can see this in case of top. So based on the location or position of source, drain and gate and OSC, what three parameter, please keep in mind how we can define top gate, top contact based on the position of gate, contacts and OSC, right? So top gate, top contact, top gate, bottom contact and bottom gate, top contact, means gate at bottom. Here you can see gate at bottom, whereas contacts are over the OSC, over the OSC. OSC is here. So why we call it top contact? Contacts are over the first deposited the semiconductor, organic semiconductor material. Thereafter, this source and gate. That's why top contact, and bottom gate because gates at bottom. In both the cases, gate at bottom. In case this gate as top, gate at top. So that's why. So based on the location of gate, source, drain, and OSC, we can define the classification of the structure. Classification of the structure. Now these here you can see this side we have explained the classification based on the position, based on the position of source and drain and gate, right? And here position of, right? These are the 3D structure, right? 3D structure of both the this now top contact and bottom contacts. So here you can see this OSC material over that source and drain. So that's why this structure is called BGTC, gate at bottom, right? Here you can see this substrate is provide the mechanical strength over that gate is deposited, thereafter dielectric, then OSC, then source and drain. So that's why this is structure called bottom gate top contact. So this comparison is given both in bottom gate top contact and bottom gate bottom contacts. So bottom gate top contact OTFT having much higher mobility in comparison to this BGBC, right? Low contact resistance. Why we call it low contact resistance? Because here you can see, right? Injection area, right? Directly, right? In between this, now adhesivity is much higher, right? In case of here, you can see this, right? Or here you can see some due to no fabrication process, due to some fabrication air gap will be there. So this have the some gap between OSC and source and drain, right? So this create the problem. Ma'am, right now I'm taking online class. Can you call after 1 hour, please? Yeah. So here, but both the structure means BGTC and BGVC have their own merits, right? So here we have merit of high mobility, but in case of this no BGVC, small channel length based device is possible. So this having the merit of in comparison to BGTC, lower channel length device can be fabricated using bottom gate, bottom contact structure. Right? So this these are the comparison between BGTC and single gate based BGTC and BGBC. Now, based on this, no, we also have gone through these devices. Right. So based on the structure here, you can see based on the structure, performance it also affect, right? So here you can see this drive current. In case of contact, right, drive current is 37 microampere, whereas in BGBC 8 only, right? These are the data, right? So you can appreciate means top contact device having high mobility because of, in case of here you can see, because this device having much higher mobility in comparison to BGTC. That's why, right? So yes, even mobility, if we can compare, mobility is much higher, right? 4.44 in this 1.11, right? So this, and threshold voltage is different, right? And the ion of current ratio also you can see here, right? So this 10 to the power 8 in case of this. Obviously, dry current is high, right? So it's directly affect the ion. So these are the reported, right? These are the results we gone through, right? So if you see the comparison between both, right? For top contact, right? ID is 4 times higher, right? In comparison to bottom contact. Mobility 3 times high, right? BT is this slightly high in case of this, but these 2 point is positive, right? We always want to BT should be low, right? And sub threshold is 50% lower. So the comparison. Yeah. So now this earlier we have discussed single gate OTFT. This you can see the dual gate, right? Organic neoprene transistor. So this be aware about that up to this, right? This you can see single gate, right? Here single gate. This your BGTC up to this. But if we can add additional dielectric and top gate, then this called your DGOTFT, dual gate. So one gate at top, so this top gate and this bottom gate, right? And this top dielectric, this bottom dielectric, right? Source and drain. So fabrication is much easier in comparison to MOSFETs. So these devices nowadays in lot of emerging fields, lot of people are working right in this area. So then, बोलिए, just just 1 minute, just
Okay, sir.
yeah. यतिन अभी तो टाइम है ना, कितना है ना?
जी सर, टाइम है सर.
Sure, sure. Okay, just one.
Sir,
दोनों विंडो कर लो ना। इनका क्वेश्चन एक था। ठीक है।
Sir, can we ask one doubt?
Sir is on hold now, present.
Okay,
Yes,
okay,
yes,
okay.
yes, please.
Please.
Yeah,
Yes. Good morning, sir.
yeah.
Sir, actually, one doubt was there. Sir, suppose we have to do this work using Silvaco TCAD.
Yeah.
So, sir, what sort of calibration technique we should opt so that we are going somewhat having resemblance with experimental work or something like that? So, sir, how
Okay.
we can do this task, like calibration of our work?
Actually, yeah, because same actually we aware about no that Shockley equation. So same Shockley equation is applicable for OTFT also. So we can apply the mathematical. Suppose we don't have the fabrication facility. So what we can initially actually during when we are assigning the work to our PhD students, so normally we go for initially to calibrate our software. No, we go for fabrication work. Initially, we select the one good transaction or good journal paper, and we go for that. Right. Initially, we validate that paper. Normally, we suggest our PhD students or MTech scholars. You initially, because we don't have fabrication facility, go for this. Uh, Validation of initially simulate the fabricated paper. So if you are approaching to that, right, and another validation is if we simulate same work, right, and we go for mathematical modeling, right, mathematical modeling, and we are approaching same fabrication work and our mathematical means analytical analysis, then we say this our simulation work is almost approaching to fabrication work, right? Then we apply same device for different circuit applications, right? So nowadays novelty is different circuit applications, right? Because a lot of work is going on in this area, especially for structures, right? So and other thing you can go through the pool and Frankel model also, right? So and if you require, I will share few, right? This uh, organic electrons laboratory in Germany, right? They are fabricating almost every month 3 to 4 devices, and their work is open source, right? You can go through their publications. So recent work you can means receive from that, right? So for especially optimization, right? Same Shockley equation can be applied. Same mathematical model and a mathematical analysis can apply, right?
Sir, I have got this thing. Actually, sir, I was basically thinking that what sort of parameters we can tune, like effective mass, mobility. We can tune these parameter, or in calibration, it is something different that we have to do so that our simulated work is having resemblance with experimental work. So, what sort of parameters actually we can tune?
Yeah. That you can note here. I actually maybe you will not. These parameters can be right. So here you can see, right? These are the performance parameter, and other is structural parameters. So two things we can twin. One is the performance parameters, right, and other one is structural parameters. So these two you can means twin, right? Performance parameter where these all no this 7 8 parameters you can, right, drain drive current, mobility, threshold voltage, transconductance, right? This with the help of mathematical, right, and other structural parameter. So 2 or 3 papers available in our in my Google Scholar where we worked on optimization, right? So please go through that. Even during my PhD, I developed the model for optimization of performance. So that paper I will share with you. If you don't have that means permission to download, right? Where mathematical model is proposed, how to optimize the performance, right? So that will help you, right?
Sure, sir. Sir, it was nice. Sir, one more doubt. It is a very small doubt. Sir,
Yeah.
actually, it is regarding to this PPT only. I think, sir, it is not so much. But, sir, it was that trans conductance and output conductance. These are the two things. So, sir,
Mhm.
how exactly we can differentiate between them? Because, sir, I have seen some papers in which they are saying that output conductance for circuit applications, it should be kept low. But for
Mhm.
trans conductance, we are always interested. It should be as high as possible.
Yes, yeah.
So, sir, how actually, what is the basic difference between these output conductance and trans conductance? Sir, if you can please tell regarding this.
Right now, I don't have that data. I can go through. Then surely you can keep it no touch with me. Surely I help you out, right?
Okay, sir. Okay, no problem, sir. Thank you, sir.
Okay. Yeah. So here, DG OTFT, dual gate OTFT, where if we compare in right single gate and dual gate, so this you can see here, right? This side. So where we compare with the operating regions, we can see here this, right? Uh, Drive current, right? For here we can see, right? Is much higher in case of DGOTFT, right? So uh, this DGOTFT, as we aware about the MOSFETs, similar way here three modes of operation are there. When we one gate is grounded, another supplied, another is top gate is supplied and ground, bottom gate is connected to ground, and if both the gate is tied and apply the supply. So all three modes of operation given in this diagram, right? Where and we got that DGOTFT in case of DGOTFT dual mode, right? When where top and bottom both the gates are tied together and applied the supply, so have higher current, drive current, right, in comparison to uh, bottom gate and top gate. So this. So and here see the comparison we compared with single gate. So drive current 5.7 times is higher in case of single gate, and mobility 3 times, right? And the BT factor of this 2.8 times. BT is in case of because if we can go for high performance, so additional fabrication cost will be there in case of DGOTFT. And here given the examples of based on the DGO TFT and single gate, this both here, right? So this reported work, and as we aware about all single gate and dual gateway, so here given the comparison between, or other words we can say merits and demerit of different structures, right? So all three structures I have kept here. So first one is the this no bottom gate top contact, bottom gate bottom and contact, and dual gate. So here you can see the merit of all three. Performance is high, right, in comparison to single gate or BGVC, right? But what is the merit of BGVC here? Fabrication using simple printing technique. Whereas in case of no top contact, fabrication is suppose we are using shadow masking is used, right, for the purpose of top contact. Whereas in case of BGTC, there's no multi-step photolithography process also apply for BGBC because top contacts. हाँ बताएं. हाँ हाँ भेज दीजिए. And BGBS, so fabrication is other words I can directly say in comparison to top contact, BGBC is having simple fabrication, right, or easy fabrication. But in case of dual gate, merit is performance is very high, right? If we compare all three structures, but demerit, this last slide you can see short channel effects are difficult, right? Or whereas performance is low in case of BGBC, and dual, in case of dual, right? The one thing is top deposition, right? Here you can see, you can appreciate this, because in case of this no OSC here, OSC is having a low temperature fabrication tendency if we apply the top gate dielectric, or normally dielectric is deposited at higher temperature. So this deposition of this uh, over the OSC dielectric, it can create or damage the surface of the OSC. So that's why both the cases, right? This OSC is if we don't have no conducting dielectric, P3, there's no PMMA, right? Polymethyl methacrylate is only a piece. Recently, people are using as a dielectric, organic dielectric, PMMA, polymethyl methacrylate, right? Apart from that, other material, if used, then that material will be deposited at high temperature. So that will affect the surface of the OSC. So that's why this word is written here. Impairment exists during top gate deposition. So this can means damage the surface of the OSC, and if surface of OSC is not smooth, that directly affect the performance of device. So here given the some few other, right, options where people can work, right? Here you can see earlier we have discussed in single gate only up to this, right? People can apply this this structures. So this called your BC ditch structure. If you can right, OSC you can deposit inside to this dielectric. Other is elevated source and drain electrode, right? So we have applied same elevated source and drain, right, here. So we compare the performance, and this will compare the performance, and we got this, right? So BC with the elevated source drain contact, right, having much higher, right, drive current, right, in comparison to normal, right, this normal and this ditch, right? So ditch having 120 microampere and this having 142. So this comparison between two. So whole concentration and current flow lines we have compared. And this another is effect of electrode thickness also have the impact on the performance. So few example. This actually I suggested recently one query I received. So this model given in my paper, right? So where earlier people reported only channel contact resistance analysis. In this our paper, we have applied the, apart from channel resistance, the analysis of bulk and contact resistance both, right? Earlier people reported channel resistance and contact resistance analysis in OTFT, but what we have analyzed in this, contact as well as bulk resistance in our that paper, that work, right? So that can also have means bulk resistance also impact on the performance. So that we have given in that paper. So here we can go through contact thickness, right? Also have the in terms of charge carrier injection, contact resistance and threshold voltage. So contact thickness affect three parameter: charge carrier injection, right? Because charge carrier injection, as I discussed in earlier also, if we don't have source or drain, right, and OSC matching material in terms of work function difference or barrier height, right, that's affect the injection, right? So that's why. So in this, right, so those who have interested can go through this work, right? Analysis of contact and bulk resistance in OTFT. And we got that on the basis of, right, thickness, this actually impact of electrode thickness. So here we have analyzed and given the summary. If we this source and drain thickness from 0 to 50 nanometer, then ID improves by 57 for BC, and because top contact will have lower impact of electrode, in comparison to BGBC, right? So that's why. So here you can see this side, right? This side, source and data, right? And different analysis is shown here, whole concentration, right? And this. And apart from that, this effect of source then on the top and bottom count parameter also. So if we can compare here, this table you can see, right? So dry current is right 10%, right? In comparison to VC 57%. If we go for right change in thickness from 1 to 50 nanometer, 1 to 50 nanometer, right? So this impact on the dry current. So in case of bottom contact, right, electrode having the right, much impact on the performance. Right? And this, what is the impact of channel on the performance? So here you can see everyone is aware about that channel extraction, right? So here in this paper we have right this given the depth analysis, right, about the impact, right, of the channel length. So those who have interested can go through this. We have published this in year 2012, right? Where change in thickness from 5 micrometer to 40 micrometer is compared. So and this model is given in this. So somebody is interested. What is the model of right contact resistance, right, and transconductance, right? So here one person. So this you can please apply this model GM, right? So maybe you can get that answer of your query, right? This mu linear CI WIL BDS. So GM have in linear region, right? And so different persons also apply given the reported same concept, right? They have right change in channel length from this. So they have reported, right? So if one Jung et al. Is reported 3 times, right, change in mobility. Yeah, last point for this effect of semiconductor and dielectric thicknesses, right, on the performance, So here we can see the impact of semiconductor and dielectric thicknesses, where thickness of OSC affects these 4 parameters. Thickness of OSC affect the 4 parameters. So same concept we have discussed, right? Here you can see, right, this source, right, and here you can see this nearby we have considered the contact resistance and near the conducting channel, right, over the conducting channel, right, this given the bulk resistance. So if we can have the means increase the width of the this no thickness of OSC, then that increase the bulk resistance, and that increase the bulk resistance, right? So channel is near the interface of dielectric and OSC, right? So that is there. So this thickness of organic semiconductor affect electric field, right? Trapped in the semiconductor also, right? Because and availability of charge carriers, right, and bulk seat resistance. So that this concept we have calculated this by changing dielectric and thickness, right? Here you can see with this diagram, right? This diagram, and this also you can see this thickness, right? TO organic semiconductor thickness. If we can increase and decrease, and you can see the equivalent diagram. If we can increase the TOSC, thickness of OSC, right? So it can means enhance the carrier injection, but that in comparison to change in bulk resistance is much higher impact. So because of the bulk resistance will increase, right? That if bulk resistance increase, obviously that have the reverse impact on the current. So that's why. And similarly, we aware about that COX is equal to epsilon naught epsilon R over TOF. So this also, so same concept, very simple concept we have applied in both the change in thickness of organic semiconductor, change in thickness in dielectric, right? So thickness of dielectric have the impact on gate dielectric capacitance, channel formation, and threshold voltage. Whereas OSC have the impact on 4 parameters, right? This side. So somebody is interested, right? They can develop the model. Bulk resistance model already we have reported. Somebody can apply for the trap analysis in semiconductor also. Right? So a lot of work is going on how to optimize the performance of organic material-based devices. So this comparison reported in our paper. So if we go for comparison between both the structures, right, top contact and bottom contact. So here you can see, right, this have the right. So OSC incrementation from 20 to 150 nanometers, so where we ID improves, right? Only not all parameters, right? But ID improve in top contact is only 17%, whereas this have much impact on bottom contact devices. Similarly, this performance parameter is mobility comparison, right, for both the structures, top contact and bottom contact. Then we have analyzed the effect on electric field. So this comparison given in variation in percentage, right? Mobility enhances by have the impact of this 22% enhancement in mobility, and in bottom contact 10%, right? When we are going to, so this we have analyzed two category, 20 to 60 and 60 to 150. Higher side, right, mobility is reduced by 18% because of this concept. Bulk resistance increased when have higher thickness of the OSC. That's why. And by the analysis, somebody can analyze, right, the impact of this. You can see here, right, impact of this by the mathematical model. So that have the impact on ion-off ratio also. And threshold voltage can be right. Mobility and threshold voltage are greatly affected by variation in TOS, right? So here you can see. Right? So if we can increase, right? So it TOSC is directly proportional to BT. So somebody can appreciate this, right? So those who are interested can apply same concept in other devices also, because this we have compared in single gate. So somebody can apply same concept in the dual gate also. Then few reported. Yes, 1 minute just. Just 1 minute, please.
Okay, sir.
Okay. Yeah, so here a few we have included for the work, right? So here effect of interfaces, right? We have not worked in during this, our effect of interfaces. So somebody can take up this analysis, right? So here one interface between contact and semiconductor, right? And another is interface between dielectric and this interface. So what the bottom gate OTFT dielectric surface treatment can be employed. जी सर ऑनलाइन ले रहा हूँ 130 सर रखवा दीजिए सर वही रखवा Yeah, so this in bottom gate, what can we apply to improve the performance? So dielectric surface treatment, right here, because this no over that dielectric treatment can be applied to employ devoid of any means damage of in OSC. Whereas some sorry, okay, fine. And in bottom gate, bottom contact case also contacts are deposited prior to the OSC. So surface smoothing is possible in the OSC layer. Yes, layer. And other on applying dielectric surface treatment, tap state can be reduced. What is the impact on the surface treatment? Accumulation of charge at OSC dielectric interface increases and dipole at interface reduces. Self-trapping of charge carrier minimize, improve the device performance. So these can be take up as a problems for the research. On applying source drain contact surface treatment, one can charge injection or extraction can be increased. Injection barrier between contact and OSC, so that have the contact resistance decreases. So these problems can be considered for the purpose of by applying the source and contact surface treatments. Right? And as for concern of structures, right, material with ambipolar characteristic would find their potential uses in the portable electronic circuits with complementary design. Right? Ambipolar, we aware about our no bipolar or unipolar or ambipolar. So especially bipolar, we aware about that one have the majority carriers and minority carriers. But in case of ambipolar, same material can have the equal kind of carriers, right? So lot of people are working to provide that. So same material can have the N-type and P-type device property. So that can be used for the be aware about the for the CMOS, right? So be aware about for the CMOS is the building block for the design of for digital designs. So in case of organic, people reported this ambipolar material, and with the help of that ambipolar, they reported the ambipolar material based devices also, right? And inclusion of modified structures, so people can take up these multi-gate structure, floating gate structures. These two is reported in the literature also, but not much. Right? Nanowire OTFT is possible, right? Vertical channel OTFT, cylindrical gate, organic FinFET. So these are the open area where people can take up their work. Another is analytical model for novel structure can be helpful to invest the performance before actual realization, because we have limited fabrication facility. So initially we develop the different models. So model can be developed for these devices. So is mathematical models can be developed for these devices. So before actual fabrication, people can see the performance of organic, right? So insertion of high doping region near the contacts may increase the performance of VG, right? Because we aware about that VG OTFT in comparison to top contact devices, bottom contact have poor performance. So this can be enhanced by insertion of high doping region near the contacts in case of bottom gate. Multi-gate structure can enhance the performance of OTFT through enabling better control over the threshold voltage over the channel. So this another improvement in stability, lifetime durability. These are the fabrication point of view, right? So improvement in stability, lifetime, and durability and reproducibility is an important challenge. Nowadays people are fabricating, this lot of organic devices, but one device and another device fabricated is not having the same performance. So that's why people are working in 4 parameters: stability, lifetime, durability, and reproducibility. Means in case of MOSFET, no, we can have the batch processing, but still people are facing the fabrication problem in case reproducibility of the devices in OTFT. So another challenge. Yeah, so one of my research scholar worked in organic light emitting diode. So I have added a few applications. These are the publications he has published in organic OTFT. One transaction recently he has published in based of organic, where he has worked in ovarian cancer detection using organic light emitting diode. So this multi-layer OLED structures, right? So here, I think those who are aware about the LED, they can appreciate this, right? So here we have aware about that ITO anode, right? Then emission layer, right? Different materials can be used for different. Then emission layer and emission. अभी मैं एक ऑनलाइन बोल रहा हूँ फिलहाल. ठीक 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 130 कर दूं. Yeah, so here anode as a ITU as a anode material, emissive layer, emission layer can be of multi-layer, right? Emission layer can be multi-layer, right? Then electron injection, electron transport layer, right? And top of that a cathode, right? So here you can see this, right? This 5-layer structure. Another layer you can see here we have added, right? Whole transport layer, right? In comparison to this, right? Here additional layer is, right? Whole transport layer. This electron transport layer, right? And this side is, these layers can be utilized for different purposes, right? So then here another layer is added, right? Two whole transport layer, right? And two this electron, right? Here only single layer, right? You can see. But what in this difference in this, two transport layer is added, right? One single, or in this case, right? Whole block layer added this place, right? Similarly, this side. So what whole block layer means that, right? Reject the injection of whole this side. So that's why. So, and based on this all 4 devices, right? Comparison you can see. So current density and luminescent, right? So this device you can see. So if we go for this device, we compare to this device, right? And see the changes in the changes, right? In the current density, but luminescent is increased much higher. Luminescent is increased much higher in case of. So somebody want have a higher luminescent, go such kind of structure, right? Such kind of structure. Here, this concept is applied for the detection of the ovarian cancer, right? In that paper, and this paper is published in the IEEE transaction. So block diagram illustrates methodology to detect the ovarian cancer. So here only what we have did, we have utilized the audit, right? Source, and that's audit as a source as well as detector, right? Only the concept we have applied. This audit, right, device is used as a, right, as a source as well as detector. Here you can see in between we have taken the sample of urine, right? Sample of this side is source and this side is detector. Before discussing this, you can see this how we can find out, right? So here you can see this OLED emits light, right, in the range of, right, or equal to or greater than 300 to 400 nanometer, right? Thereafter, emitted light is right, excitation for urine, right? Urine pass through that light. Then urine starts fluorescence emission, right? That urine have the concern, right? That property, right? So when we drop the light source of the LED, that urine starts fluorescence, right? Emission. Thereafter, OLED detects urine fluorescence, right? Yes, and wavelength detection through OLED as a current response, right? If it is, right, is urine emission, right, is this no wavelength is equal to 440 nanometer, right? If yes, then that detected the, right, ovarian cancer. If no, person is healthy. So this comparison of wavelength, all right, comparison of wavelength, right? So given here, right? So this paper is available in the right, and somebody want okay can apply their concept in no same ovarian cancer concept in other diseases. They can work in this, right? So here you can see now, right? So this excitation of the right OLED or source, right? This source having the wavelength of 300 to 400 nanometer, right? And that, right, exciton to through pass the this no urine sample through that, and this side detector, right, of the so emission here you can see emission, right, from the urine, and measure the wavelength of that. So just very simple concept. Those who are interested, please go through the depth for this kit of right available on IEEE transaction. So title I will say. Similarly, we have right. So photo generation rate in triple, right, whole block layer OLEDs device. Right? So here you can see this concept. So these are the diagrams we used in the that detection in ovarian cancer. So you can see this peak. We got the peak at in between this, no? You see, right? So this range of wave. So available photocurrent, right? So if it is in terms of photocurrent, right, and the optical wavelength, right, or cathode side, so same, right? So this. So we compare both, right, and got that. So this be aware about that device C and D, right? So this concept on the exciting, right? Exciting urine sample at 300, right, to 370 nanometer, it shows a fluorescence peak, right? At you can say 420 nanometer for healthy person, this is standard, okay, and 440 nanometer for, right, unhealthy person on chorological patient, right? At 420 nanometer, it shows a dip because of the lacking of the, right, pyridoxic acid. Because we are the electronic person, so we've taken the help from the one, right, this bio person, right, pyridoxic acid, oncology patient, and increased emission at 450, right, suggests high concentration of the petridines, which is normally observed in the ovarian cancer. So that is the concept we have applied for the light source. So another is just multi-layer solar cell, right? Here, everyone, I think this is very simple, right? So we just opposite of the OLED concept. A solar cell is an electronic device. We directly convert sunlight into electricity, right? Sunlight shines on the cell, right? Photons, light particles bombard the upper surface of the this sunlight, right? And that generates the electron hole pair, right? And this side you can say anti-reflection we have quoted, and front contact electrode, then this base material, then rear contact. The photons give up their energy to electrons. The electron uses this energy to jump across the barrier, escape out into the circuit. This process requires material in which the absorption of light raise an electron to higher energy state. And followed by the movement of this higher energy, right? This you can see external load, electron from the solar cell into external circuit. This. So in this electron hole pair is collected right through the electron. So based on this, actually one of my students is worked on these materials and given the right. So XRT results right, patterns show no sharp peak, the absence of peak listed amorphous nature. So this material we have developed in semiconductor amorphous laboratory at triple NLT for the solar cell application. So that is the contribution of this. Other concept is everyone is I think aware about it. And same material we have applied for the as a observation layer right, in the other material we have taken standard materials right purchased from that and this material level right developed in the laboratory right? And these are the results. This paper is accepted right this and these are the parameters for accepted for different materials right? All three materials and all three parameters be aware about the solar cell performance can be defined by open circuit voltage fill factor short circuit current and conversion efficiency right? So these are the display right? Applied lot of work is going on in this area. So thank you very much, everyone, for patience. Right? Thank you very much.
Thank you, sir. Hello.
Yes, please.
Thank you, sir. After a very busy schedule, sir, you have taken the time for us, sir. Thank you very much, sir. And your topic was wonderful. I think that most of the research students those are involved in research work, that they will be benefit by this presentation, sir.
Yeah.
And
Thank you,
also you have
Yatin. Really, it's my pleasure to be here. Really, because you have 1 week back or 4 days back, you contacted and immediately because really I'm also happy to share my knowledge.
Nice. Yes, sir. We have shared the topic about the inorganic semiconductors and organic semiconductors and its applications also, sir.
Right.
That was very useful for the person those who are in the research work.
Right.
And also you have shown the applications also, and most of all you have also emphasized on the organic light emitting diodes, sir.
Yeah.
And one more interesting topic was that is the organic thin film transistors.
Yeah.
Most of the persons are used to work on the
Silicon.
FET and the silicon insulator,
Yeah.
but lesser number of emphasization is here in this sector, that is organic thin film transistors. I think that there are heavy scope is here.
Yeah.
And with your permission, sir, I'm also getting a request to share your slides, sir.
Yeah, surely I will really share with you.
There is a heavy request to share the slides, sir, of yours, sir.
Yes, I will share. Surely I will share Yatin with you, right?
Yes, sir.
Sir, sir, one thing, sir, as we have seen in this, as an accumulation region, we have seen in these slides. So, sir, as in N-channel MOSFET, we are having accumulation, depletion, then inversion. And inversion further, we are having weak, moderate, and strong. So, sir, can we say the sub-threshold region, it is same as weak inversion region, or it is different?
It is actually different because in this, we have don't have the bulk channel, right? Bulk kind of thing. That's why. Only if you go through them, right? Always in MOSFET we have source drain, right? Apart from that, bulk connection also. So that is that kind of structure is not used in this, right?
Okay, sir. Okay, thank you, sir. Thanks, sir.
Right.
So one more thing I would like to appreciate that in your slides, sir, you have concluded that included that all the characterization parameters and the design parameters, even the design issues also, even the contact potential also. You have gone very minutely in deep
Yeah.
in all the design issues, sir. Thank you, sir. Thank you very much, sir, for this wonderful session, sir.
Yeah, thank you.
Any questions from the audience, please?
Yes, please.
Hello. Any questions from the participants?
Yes, sir. Good afternoon,
Yes,
sir.
Yeah, good afternoon, please.
Sir, your presentation was very nice. I have one doubt. In this organic thin film semiconductor, you said that the area of MOSFET is comparatively a little bit more. So, is it not possible that because the area is more, the power consumptions may increase in these cases?
Yeah. Yeah. Yeah, actually, that's why I initially told that a lot of opportunity, right, for the optimization or compactness of these kind of right devices. Initially, even this right devices we have gone through 5 micrometer to 40 micrometer, but
Yes.
recently, last 2 or 3 years back, a few people is reported around 100 nanometer, right? As we please earlier also I told, because lot of people are working in silicon based, hardly means they are working on 5 nanometer, 7 nanometer, and 8 nanometer, 10 nanometer in research in silicon based devices. But in case of right OTFT, if we want a high drive current, so high drive current can be possible either we have means large width, right, and large dimension of the device, right? So we can,
Yes.
that's why the voltage, right, supply and dimensions of high in case of, so we can either we have higher supply voltages than we have, right, simply Shockley equation, right. If we want okay high IDS, then what we can do in the equation, either we can have high capacitance, right, and high BGS BDS, then we can have high. So that's why dimensions of these devices. So people are what actually people are working, chemistry person, physician, physics persons are working to develop new organic material with
Yes.
high mobility, like CNT. CNT people reported almost 800 means centimeter square PS mobility, or 5,000 8,000 also. If we can apply that material in this no OTFT, so people can go much lower dimensions and much lower voltage supply. So that is there still.
Yes. Because what I feel nowadays,
So that is
power consumption is the
Yes,
highest
obviously.
area
Yeah.
which should be focused.
So that's why initially, if we gone through, I compare with performance and cost. So
Yes.
if our target is cost is much lower, then go for organic based. If your target is low power, right, and means low power, high speed application, go for silicon based.
Yes.
Then you don't go for organic devices.
Sir, can we say that with a bit of a little bit more experiments, we can have exact optimization in this?
Yes, exactly.
Yes.
And people really, because a lot of work is going on this, because of the fabrication is much means easier or low cost. So that's
Yes.
why lot of work people are working for, because means as on date, other words I can say, as on date, one person cannot survive. Nowadays, research is a multidisciplinary research. One person from mathematics, mechanical, electronics,
Physics.
chemistry, physics. Then the group of people can work. Then they can come up with a good solution.
Good solution. Yes, sir.
Yes.
Thank you, sir. Thank you for a fantastic explanation, sir.
Yeah.
Thank you.
Sir, one more question is there from Avinash Kumar Pal from Lucknow, sir.
Yes.
Please, Avinash sir, please raise your question, sir. Avinash sir. Avinash Kumar Pal, sir. Avinash sir has raised a question that can we use OTFT in nano design?
Yes, that device
Yes,
actually
you could
only
please.
as we aware MOSFET and CMOS, right? Switching device. Similarly, this TFT also is switching device. only what actually their requirement according to that. If they want, okay, nano device for display application, nano material based device for display, then surely use as a backplane driver, surely.
Any more questions, Aminat sir? His mic is not working. Okay, so he says thank you, sir, to you.
Okay, thank you.
And from my side also, thank you, sir, for
Yeah,
having a wonderful discussion also with all the participants, and they are raising questions, you are answering for them, sir. Thank you, sir.
Thank you. Should I leave now?
Yes, sir. Yes, sir.
Thank you.
Thank you, sir. Next session is going to be of Dr. Sanjeev Rai. He is a professor. He is associate professor at MMUT. He is also going to discuss about the VLSI only. In the field of VLSI, his topic will be the recent trends in VLSI design with leakage control and low power design issues. He's also going to discuss about the VLSI designs only, simulation parts and the fabrication part also. So we will be back in at 2:30 p.m. Till then, hello? Hello? Am I audible to you all?
Yes,
Okay,
sir, you are audible.
Sir.
Okay, then we will be back at 2:30 p.m. We will going to head with the expert talk on VLSI design issues regarding to the controlled and the leakage current and leakage control problems in VLSI designs, in simulations and the fabrications also. Please fill up the feedback form also. It has been already sent in the